In this video, I want to show you an example problem where the ideal gas law and gauge pressure is shown so that you can understand these things for your physics or chemistry classes. What's going on, everybody? It's High Peak Education coming at you with another video, and stay tuned till the end because we're going to discuss how your tires are inflated, how you can know if they're overinflated or underinflated, how you can know if you should over or underinflate them in the summer versus the winter, and how to check these kind of things. So let's get into today's problem. The gauge pressure in your car tires is 2.8 times 10 to the 5th newtons per meter squared at a temperature of 35.0 degrees Celsius when you drive it onto a ship in Los Angeles to be sent to Alaska. What is the gauge pressure in atmospheres later when the temperature has dropped to negative 38.0 degrees Celsius? Assume the tires have not gained or lost any air. It's way too big, right? So in other words, remember, Earth is one atmosphere, okay? I mean, by definition at sea level. Now, I mean, Venus, probes that have been sent to Venus say that, like, the atmospheric pressure near the surface of Venus is like several Earth atmospheres. I don't remember what it is, but it's something like 7 to 12 or something. But point is, it just gives you some sort of like basis on like, okay, how many times is it that of Earth? Venus has a dense atmosphere, has a bunch of clouds and all kinds of stuff. But point is, like, you know, the moon has basically no atmosphere, but, you know, Jupiter has an atmosphere. And the point is, like, gases definitely create pressure, okay? So certainly that answer is way too big.
Right.
So we need to make sure we're in the right units and we're answering in atmospheres, okay? So that's the first thing. Second thing is, let me ask you, what is the definition of pressure? We talked about this briefly as well before.
Right. So is it the amount? Like density is the amount of molecules per cube.
Mm-hmm. That's right. That's right.
But it's not, and it's not how fast they move.
Not exactly, right.
Yep, that's what I'm about.
Okay, no worries. That's fine though. So let's talk about this in a little bit of detail, because given this is a gas law question, I'm assuming you're going to see some gas law questions, and we should discuss this a little bit to understand the differences. So let me go back over to the board, and I will, let's see, create a cube here. And let's imagine this cube is what we often call a parcel of air. Now, a parcel of air is just a fancy way of saying it's just some imaginary box of air, okay? So it's like, now, by the way, usually parcels of air, we say they're big enough to have many molecules so that there's like a good mix. Everything's like, in other words, it's not so small that it's all nitrogen, right? We gotta have some nitrogen, oxygen, argon, and everything. But it needs to be small enough that it only has one pressure, temperature, and density and volume, for that matter, for the whole box. So it's kind of like it's sort of an imagination thing, but like you can imagine like it's big enough, a bunch of molecules, small enough that like it has all those things the same. So again, it has some pressure, some temperature, and then some density, and then some volume. Now, okay, so the volume is what for this thing? Right, so it would just be like length times width times height, and that would just be meters cubed, okay? So density, like you said, would be if there's a bunch of air molecules in here, and they're all bouncing around, the density is just going to be the mass of the gas divided by the volume, right? Think of density as how concentrated the gas molecules are. So again, so density, and again, the units are going to be, at least in physics, it's kilograms per meter cubed. I think you and I have discussed before, in chemistry, it's most often they use grams per centimeter cubed. Okay. Now let's talk about pressure and temperature. Temperature, just like you said, is related to how fast the molecules move, okay? There's actually an equation in which you can relate temperature to kinetic energy.
Okay.
So I think it's something like 1/2 m v average squared is equal to 3/2 k subscript b times T. And you know what this K is? It's actually important in gas constants. This is called the Boltzmann constant, okay? So the Boltzmann constant just tells you, like, how much energy do you have per every 1 Kelvin, basically. So the Boltzmann constant will be units of joules per Kelvin. Oh, and by the way, temperature, of course, then has units of Kelvin, at least the SI unit, right? But now let's talk about pressure. So remember, how fast each of these is going to have a slightly different speed, right? But there's some notion of, like, this is an average velocity, or average speed, I should say, because the direction is all over the place. But average speed gives us the notion of temperature. But then pressure is going to be different. So pressure is going to be, first of all, the equation, F divided by A. So what is F and what is A typically in physics? Yes, it's going to be force divided by area. Now you may say, what force and what area? It's like molecules in, like, a box. Well, the force, it's the force from the molecules, and the area is the area basically of the side walls. So that's why it's like an imaginary box. So it's like of the sides. And again, that's why you sort of imagine this parcel of air. Now, by the way, if you're actually talking about a like a tire, if you're actually talking about like a real object, so there'd be a bunch of air molecules everywhere inside the tire, right? And, you know, so they're just kind of randomly everywhere. But the point is, they're all going to be hitting the sidewalls of the tire. So they're all going to be exerting a force on the outside of the tire sidewalls and on the inside of the tire sidewalls. They're going to be basically bombarding the sort of the skin of the tire, if you will. Okay? So that's kind of the pressure. Now, by the way, that leads us to what units for pressure. What's the units of force? Yes. Yeah, meters squared. Exactly. Because if volume is in meters cubed, area should be in meters squared.
Right.
Now, one more thing I should briefly mention. Newtons per meter squared is sometimes just how people write the unit, but it's also written as the unit PA, which is what unit? Pascals. You may have heard this before. Okay, so 1 Pascal is 1 Newton per meter squared. Now, Pascal is the SI unit for pressure. One more thing, and this is important, like, just for semantics. Like, pressure more than any other variable, like I've taught physics for a number of years, more than any other variable, has many, 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 many units. Like, more than any other thing I've seen, it has so many units. Like, people use atmospheres. You and I have already discussed this. People use hectopascals. A hectopascal, by the way, is what we call a millibar. A millibar would be like used on weather maps. People use torr. I don't know why they still use that. People use inches of mercury. Like when you go to the doctor and you get your blood pressure taken, that's like inches of mercury units. They say, like, you know, whatever it is, 120/85 or something, right? It's like, what are those units? That's inches of mercury. That's because in the old school days, barometers used to have a certain height. Probably more detail you need to know. But the point is, pressure has many, many units. So we need to make sure we're in pascals, or for that matter, newtons per meter squared. But then at the end, we're going to convert back to atmospheres. Is that clear so far? Okay. Now, let's do the next thing then. So the next thing is the following. Let's talk about gauge pressure. And I know we discussed this again before we parted ways. So do your best as far as you can remember what is gauge pressure. Suppose I take the tire off the rim. Okay? So you've seen people bounce tires around like in the tire shop or whatever. When those tires are bouncing around, you've still got the inside wall and the outside wall, right? Is the pressure on the inside 0 if the gauge pressure is 0? If that tire's off the car, does that mean when the gauge pressure measures 0, does that mean there's no air in the tire? So the idea is that gauge pressure has to do with the difference. So the idea is that if gauge pressure is 0, the pressure on the inside of the tire equals the pressure of the atmosphere. Like, in other words, if you have a flat tire and your tire is completely flat on the road, you just have 0 gauge pressure. I mean, your tire's not helping you because it's not inflated. It's just the same as the atmosphere. So the gauge pressure, first of all, is basically it's the pressure above. This is important. Above, I'm having trouble writing here. Above atmospheric. Okay, so conceptually that's what you want to think about. It's the pressure that's above the atmospheric. So usually when we inflate a tire, it's above atmospheric, right? It's a positive gauge pressure. By the way, is it possible to have a negative gauge pressure? Suppose you have vacuum sealed peanuts. Put a little pressure sensor in there, open it up. You know, they sucked out the air from there, right? It's less than atmospheric. Okay, so there you go. So the thing is, gauge pressure is the pressure that's absolutely in the tire minus the pressure of the atmosphere, okay? So the idea is that, like, let me just be really simple. Suppose the gauge pressure was 2.5 atmospheres. That would mean the absolute pressure is 3.5 atmospheres. And that's because normal atmospheric pressure at sea level is about 1.0 atmospheres, right? So that would be, you know, the gauge. That's what our little pressure gauge would measure, right? Okay, so I'll just delete those, but you get the idea. Okay, so with that in mind, we have to, now think about this. Does the ideal gas law care about gauge pressure, atmospheric pressure, or absolute pressure? Absolute pressure, because that's like, you know, how much pressure is actually in the gas. Okay? So the first thing we need to do is we need to take this and solve for absolute pressure. So for this particular case, we can say that the absolute pressure is equal to the gauge pressure plus the pressure of the atmosphere. Now, the gauge pressure we already have, that's 2.80 times 10 to the 5th. And then, by the way, newtons per meter squared, that's pascals. Same thing. We could just, it's more shorthand. Plus atmospheric pressure. Now, atmospheric pressure, this is a good number to know or to just look it up in a book. Atmospheric pressure for Earth is at sea level. This is at sea level, which is usually where the standard is about 1.013 times 10 to the 5th pascals. Okay, that's just a number you can look up. Okay, so you can put that right here. Okay, and let's go ahead and add those together. So basically we just need 2.8 plus 1.013, right? Because everything else is times 10 to the 5th. So I think we've got 3.813. So that's the absolute pressure of the air in the tire. Okay, so now, if that's the absolute pressure in the air in the tire, then what we can do is we can start thinking about the ideal gas law. Okay? Now, when we think about the ideal gas law, temperature needs to be in what units, like we just discussed. So newtons per meter squared, though, is the same thing as pascals. Remember, a pascal is a newton per meter squared.
Well, technically I'm not wrong.
Yeah, but I'm asking you, what units does temperature need to be in? Right. So first of all, we need to take these temperatures. So we need to say the temperature of Los Angeles, we need that in Kelvin. And we also need the temperature of Alaska in Kelvin. So let's do those conversions. What do you add to Celsius to get Kelvin? 273, exactly. Okay, that's a good number to know. So this is 308 Kelvin, and then Alaska is, let's see, negative 38, 230. I got 235. Did I?
Yeah, 235.
235. Okay. All right. So that's another thing. Now, when we say assume the tires have not gained or lost any air, what are we assuming is the same in the ideal gas law? Before and after. Not the same pressure.
The pressure is going to be different.
Mm-hmm.
I know that they're both
Yeah, but how are they blown up? Like, what stays the same if they haven't lost any air? So remember what the ideal gas law looks like. So you got volume, right? And let's also assume what else is the same. Remember what the ideal gas law looks like. PV equals nRT. Right, the number of moles, right? Suppose there's, I don't know, I'm not a chemist, but say there's like 5 moles of air in there. It's 5 moles of air afterwards, right? We haven't leaked out. So the N is the same. So this is kind of the idea, right? We've got this. Now notice, by the way, since this is a constant, V, and then these are constants, what we can do is we can get it all in terms of one constant. Now let's think about how we might do that. We can rearrange this to say P over T is equal to NR over V. And we don't really care
right.
the number of...
We don't really care about that, so then we can just do P over T equals P over T.
There you go, exactly. So we can just say P... Exactly. So the pressure at LA over the temperature at LA is equal to the pressure at Alaska over the temperature at Alaska. You agree with that? Then it's just a matter of algebra. By the way, I think this is, don't quote me on this, I think this is called Charles's law. When the gas laws were being discovered, there's like Boyle's law, Charles' law, Guy Lussick's law. I always forget which one this is. I'm 80% sure this one's called Charles' law. But in any case, yay for Charles. So we can get the pressure at Alaska, right? That's what we want. So we can cross multiply, or we can just multiply everything by T at Alaska, right? So I think this is going to be, let's just rearrange this. So I think it's going to be the pressure at Alaska is going to be, let's get this right, temperature at Alaska divided by temperature at Los Angeles times the pressure at Los Angeles, right? Because if you cross multiplied and divided by TLA, you'd get this, right? Okay. All right, so all looks good. So we should be able to put the numbers in and get the absolute pressure in Alaska. So we need 308 Kelvin. Oh, sorry, I did that wrong. 235. Yeah, sorry. 235 Kelvin. There we go. Over 308 Kelvin times the absolute pressure. So that's this number up here. 3.813 times 10 to the 5th pascals. Okay, so let's go ahead and get that number for the absolute pressure in Alaska. 2909, yeah. Let's just do 2909 times 10 to the 5th, right? Yes. Okay, so everything here with the pressure, by the way, is 10 to the 5th. By the way, pressures in pascals tend to be very large numbers. Do you see why people prefer usually to work in atmospheres or millimeters of mercury or that sort of thing? By the way, I didn't even mention one of them. You know what the most common one in the United States is? The most common one in the United States is pounds per square inch. You probably have seen this if you use a tire gauge. That the tire gauge says PSI. If you look on the tire, yeah, it says pounds. But pounds is force over a square inch, right? And a square inch is just a small, square on the edge of the tire. So anyway, but the thing is, again, people tend to work in other units, but to do calculations, we have to stay in pascals. Okay.
Okay, so then what would that be in ATM?
Well, not quite there. we want the gauge pressure. So first of all, how do we get the gauge pressure in pascals? So we need the Alaska gauge pressure. What do we have to subtract? Exactly, we have to subtract off the pressure of the atmosphere, right? So let's do that. So we need that same number that we have here shown, minus 1.013 times 10 to the 5th. So I've got, let's see, 1.896 or so. Is that what you got? Times 10 to the 5th. Okay. Then we need to get that in atmospheres, right? So finally, let's just call it ATMs is equal to the pressure at Alaska, that's the gauge pressure, divided by the pressure of 1 atmosphere. And remember, the pressure of 1 atmosphere is the 1.013 times 10 to the 5th. So keep that same number in your calculator and divide by 1.013 times 10 to the 5th. Is it?
Yep, that's right.
Okay, good. Now let's just make sure this makes sense. Let's go back to Charles' law here briefly.
No, okay, yeah, sorry.
Oh,
I go to my computer. It wait.
Oh, okay, sorry. But I was just going to briefly say, so the absolute pressure, or sorry, the temperature went down.
No.
So the absolute pressure in Alaska went down because the temperature went down. So the absolute pressure went down. So it turns out that the gauge pressure is smaller than it used to be. And by the way, we can check this. When you know the way we could check it? 2.80 times 10 to the 5th, that was the original gauge pressure. If we took that,
by 1 point
right, right. If you do 2.8 times 10 to the 5th, divide by 1.013 times 10 to the 5th, I've got 2.76 atmospheres. So the tires were originally at 2.76 atmospheres, but now they're at 1.87 atmospheres. Yeah. Now, if you think about that, that's actually a kind of a bad thing, right? Your tire could be perfectly inflated, and you go somewhere cold, and it's entirely flat. Right. It does happen a lot. I mean, if you have big temperature changes, so you have to watch for this. Yeah. Okay, so that was kind of a long problem.
On my car with such low pressure for a long time when I shipped my car from Colorado to the East Coast, and I was
okay.
Well, that sucks.
Yeah, I mean, it is a good idea, especially if you're changing altitude and temperature, and if it goes from winter to summer. A lot of times the mechanics recommend you sort of underinflate in the summer because it could get really hot, but you sort of overinflate in the winter because it could get really cold, right? So what about you? After seeing this example problem, how are you going to change how your tires are inflated or other things are inflated? Perhaps when I inflate a tube and I go into the cold river, maybe should I overinflate it or underinflate it? Let me know down in the comments how this is going to change your way of doing things. Thank you for watching today's video. Please smash that like button if you enjoy this content. Please share this content amongst your social networks to grow the channel. Please ring that notification bell to get notified about our latest videos, and I look forward to seeing you in the next video.